Accelerated failure time and Cox proportional hazard are the two most popular methods to conduct regression in survival analysis. In this video, we are going to look at some of the main differences between the two methods. I've made videos about both methods on my channel, which I'll link to this video. If you want more information, you should check them out. We'll summarize the differences in a small table. The first and major difference is what's actually being modeled in each regression. In AFT, we model the survival time, x, directly, or more often, the log of the survival time. We relate this quantity to a linear predictor with coefficients beta, covariate z, and some noise, epsilon. In CoxPH, on the other hand, we model the hazard function, which is a distribution-like quantity, meaning that for a given hazard, the distribution is completely defined. This is subtle but noteworthy. In AFT, we model the realization of a distribution, and in CoxPH, we model the distribution itself. The way we model it in CoxPH is by saying that the hazard is equal to some baseline hazard times a function of the covariate, most often the exponent of the linear predictor. A direct consequence to this way of modeling is that a positive beta in AFT means we increase the survival time, while a positive beta in CoxPH means we increase the hazard, which corresponds to decreasing the time. So the interpretation of the coefficients must be accounted for. Also note that beta 0, the intercept term, is modeled in AFT but is swallowed into the baseline hazard in CoxPH. The second biggest difference is the type of modeling that we do in each regression. AFT is a fully parametric model, while CoxPH is only a semi-parametric model. Let's understand what is meant by non, semi, and full parametric modeling. The exact definition of these are a bit contested. I'll try to give my intuition on the matter. Non-parametric means we don't assume any parameterized model. The estimates are purely data-driven. An example for this in survival analysis is the Kaplan-Meier estimator. There is no confined set of parameters like betas that we are trying to model. The terms here, the d's, which are the number of events at a given time, and the y's, which are the risk sets at a given time, grow with the data. If we have a small amount of data, we will have a small amount of d's and y's. And if we have a lot of data, we will have a lot of them. Fully parametric means we are completely specifying the model, and in our context, it also means we have a distribution. AFT is an example of this. The data is assumed to come from some distribution, like Weibull, log logistic, log normal, etc. Sometimes the distribution is implied. That is, if we add a Gumbel noise to the model, it results in a Weibull distribution. Note that given a distribution and confined set of parameters, in this case the betas and the b, we know everything about the data, and it doesn't matter if we have little data or a lot. Semi-parametric is a hybrid of the two. It's part model, part data-driven. CoxPH is an example of it. We model part of the hazard function, but leave the baseline hazard unspecified. We can either assume a form for the baseline, which implies a distribution, and then we're back to fully parametric, or use non-parametric data-driven estimator like the Breslow estimator, which is what is usually done. The fact that the AFT is fully parametric makes it more powerful, and the fact that CoxPH is only semi-parametric makes it more robust. This is an inherent trade-off in statistics. The more assumptions you make, the more power you get if your model is true, but the less robust your model is to miss specification. A parametric model has the benefit of being more powerful. Power means estimating the parameter correctly, or knowing if it's significant or not, making less mistakes, etc. But this advantage only applies if the model is actually correct. If the model is incorrect, if it's misspecified, then we could be worse off than if we used a more robust method like a semi-parametric. A semi-parametric can be thought of as a compromise. We won't get as good results like a well-specified model, but we won't get as bad results as a misspecified model. Here you can see the results of an experiment I made. The true data comes from an AFT regression with a Weibull distribution. One binary covariate affects the results, and so we would expect to see a significant p-value for that covariate. Not surprisingly, when we model the data with an AFT model that assumes the correct Weibull distribution, we get the smallest p-value, that is, the best results. When we model it using a log normal distribution, we get a non-significant p-value, meaning bad results. The model failed to detect the effect of the covariate. The CoxPH model gives a compromise between the two. It's not as decisive as the correct model, but at least it manages to detect the effect. The distribution of real-world data is never known, but always assumed. It might resemble one distribution or the other, but we never know for sure. And robustness is one of the reasons, if not the main one, for why CoxPH is by far the more popular method of the two. It requires less assumptions, and it is usually good enough to detect true effects. The next difference between the two methods is censoring. AFT can accommodate for all types of censoring, right, left, and interval, while the original CoxPH can only accommodate for right censoring. Right censoring is when a subject experienced the event after some cutoff time. Left censoring is when the subject had the event before a cutoff time. And interval is when it had the event in some time window. In all cases, we don't know exactly when the event took place. Since AFT uses the full likelihood, there is no problem. We can incorporate the information of all types of sensor data. For right censoring, we will use the survival function. For left, we will use the CDF. And for interval, we will use the integral of the PDF in that interval. CoxPH, however, uses the partial likelihood, which was developed for right censoring only. Here you can see the definition of the partial likelihood. It relies on taking the risk set, that is the number of subjects who still didn't experience the event by a certain time. But how do we define the risk set for left or interval censoring? We could throw away left sensor data and take the left interval for the interval censoring and treat it as right censoring. But this does not really incorporate the information given by these observations. I should note that there are extensions to the CoxPH which do account for left and interval censoring, but they are not as widely used as the original CoxPH. Finally, I want to show you how to decide visually which model better fits your data, at least for the simple case of having one binary covariate. In AFT, we could do a general plot or individual plots, and in CoxPH, we could use the log-log plot. Let's start with CoxPH. Under the CoxPH assumptions, we can derive that the log cumulative hazard is actually equal to this expression. Note that the log cumulative hazard is equal to the log of the negative log survival, so we could plot either. This is why this plot is also called the log-log survival plot. So for this model, if we plot the log hazard versus time, we should see an additive vertical difference between the graphs. Here's an example of such graph for data that actually came from a CoxPH model with some arbitrary H0. You can see that for most part, the two lines have about the same additive difference between them. The general graph we could use for AFT is the regular survival versus log time. As already discussed in the AFT video, the effect of beta should be multiplicative. So we should see a multiplicative difference horizontally between the graphs. For this data, beta is equal to log 2, so we should see the difference is always a factor of 2. Multiplicative difference is a bit challenging to spot. If we take the log of the time on the x-axis, we should see an additive difference. This is the graph for the same data. For AFT, there are also individual plots we can use depending on the distribution we assume. If we assume a Weibull distribution, then following some derivation, we can get the following. So if we plot the log of the cumulative hazard versus the log of time, we should see two parallel lines. And for log logistic distribution, we would get this derivation for the log of the survival divided by the CDF, which is called the failure odds. And so if we plot the log failure odds versus the log of time, we should also see two parallel lines. The accompanying notebook has all the code needed to reproduce the results and the graphs shown in this video. Well, this is all for now. I hope it helps you decide which model better fits your data. See you in the next one.